Good afternoon, guys. I'm getting. The example classes are yesterday, especially the one from 5 to 6 yesterday. The very few people came to that class. I'm really getting disappointed with the number of students coming to the example classes. Right? I know you're going to have a long break now after this week. When you return after the Easter break, you'll have week 10. I think I mentioned this yesterday also, but let me repeat what I said again. You will have a revision class on the 25th, which is a Tuesday. Then the test will be on the 26th, Wednesday. And also in week 10, we will complete the syllabus for this course. And the marks and the feedback for the test will be, I will personally email you as I have always done to you within about 24 hours. And in week 11, we will have the week 11 and week 12 will be revision classes for the final exam. The date for the final exam is not out yet. As soon as I know the date, I will let you know, guys. Okay? You probably remember at the beginning of this course, I mentioned to you about a bonus question. Do you guys remember that or no? Yeah. And that's going to be worth 2 marks, right? And that will be emailed to you again personally. I will email the bonus question to every one of you, and the question will be different for different students, right? So the question that you will get will not be the same as the question your friend will get, right? So I will email the question to you in week 11. And you should return the answer to me. I will give the details about how you should return the answer to me. All right, I will tell you later. All right, and in week 12 also we will have a revision session, revision classes to prepare you for the final exam. All right, guys. So this is pretty much what I said yesterday. I think, except I didn't mention the bonus part yesterday. All right, now let's return to. Let's return to where we were yesterday. Remember what I talked about. The last thing I talked about is this one here, right? This is what I talked about yesterday, guys. You should remember that you're testing for equality of means when the variances are unknown and not equal, right? And in this case, you have these 3 different tests, and these are the 3 different rules for rejecting the null hypothesis, where nu is given by this formula, this long expression. And these tests are based, as I told you yesterday, these tests are based on an approximation. Therefore, they are not most powerful tests because of that, right? And I also sent an email to you guys yesterday. I hope you all got it. The exact test for these cases have been derived only this in 2017, and I sent you a copy of the paper, a link to that paper, which derived the exact test for these cases, right? Which does not assume any approximation. So if you read the paper yesterday or today, you would see the exact way to test this hypothesis without assuming any approximation, right? All right. Now, the next thing I'm going to talk about is the following. Testing equality of proportions, right? So suppose So you have two random samples. The first sample is a random sample from the Bernoulli distribution with parameter px. X is the subscript. And the second one is a random sample from a Bernoulli distribution with parameter p sub y. Okay. Okay, we're going to assume the two samples are independent of each other. And I'm also going to assume that the sample size is m and the sample size n are greater than or equal to 25. The reason for this will become clear in a minute. Okay. Now, as usual, there are three different hypotheses you can test for. The first one is the two-sided one. The second one is the second one, and the third one is all right. These are the three possible tests. Right now, I'm going to write down the rules, and I'm going to write down the rules for each of these. Right. The first is right. This is the rule for the first hypothesis. For the second one, sorry guys, sorry. All right, this is the rule for the second set of hypotheses, and for the last set is all right. Now I'm gonna. These are the three rules. Now let me tell you something, because these tests are these tests are based on certain approximations, right? As you probably already guessed by now, right? they are based on the approximation that x bar has the normal distribution with parameters px, comma px 1 minus px divided by m, right? And also the approximation that, so I should put a dot here, meaning that it is, I'm sure you know this notation, guys, by now. It means approximately distributed as, right? So, and also y bar right? So the rejection rules I have written down are based on these two approximations. Hence, they are not most powerful. Remember, the two words most, the words most powerful means that the tests are derived using the Neyman-Pearson lemma, right? But because these rules are based on certain approximations, which are not exact results, these rules cannot be most powerful tests, right? Okay. Now, however, one should be able to I will give you this as homework. Let me call this let me call this 22, 23, 24. So this is I mean, you have 3 weeks of break, guys, so you should have plenty of time, right? Unless you are going away somewhere. I mean, anyway, I would like you to derive for the test 22, 23, and 24. I should say derive the approximate. I should say the approximate, because obviously you cannot derive the exact power function. I mean, the power function will be an approximation because you're assuming the rejection rules are based on certain approximations, right? Okay. Okay, so I can give you a hint, guys. As I said, I'll give you a hint. Using these two, right? So if let me call this star, right? By star, right? We can see that x bar minus y bar will have an approximate normal. Remember, you should have two independent, I mean, this is stuff we did in week 1, I think. You should have two independent normal variables. Then their difference is also a normal variable. You guys remember that? Yeah. So x bar minus y bar will have a normal distribution with parameters Yeah, you get this. This is, you should look back. You should look back in week 1, guys. You will know this result. And further, you can approximate this further. You can approximate this further by you see what I've done here, because from this step to this step, what I have done is to replace the px and the py here by x bar and y bar respectively. You can do that because, you guys remember, okay, let me put this in red. Do you guys remember what this stands for? What SLLN stands for? It stands for sorry. Yeah, we can say that x bar is approximately equal to px and y bar is approximately equal to py. SLLN stands for the strong law of large numbers. I'm sure you've done this in your... Did you heard about this, guys, before? No? I'm sure. You must have done this in probability 1 or 2. It's known as the strong law of large numbers, which says that you should take the limit, you should take in distribution, right, the limit of the sample mean as m goes to infinity is px. Right? So this approaches this as m goes to infinity, and this approaches this as n goes to infinity. So if m and n are large enough, usually in statistics we usually consider anything greater than 25 or greater than or equal to 25 as being large enough, right? So if m and n are greater than or equal to 25, then you can approximate x bar by px. Well, you can approximate px by x bar, and you can approximate py by y bar. So that's the reason. Let me put this in a box, guys. This is why this is how I got from this step to this step, guys. I have replaced the px here and the px here by x bar, and py here and the py here by y bar because of this argument. Is that clear, guys, or no? Yes? Some of you seem lost. No? It's a loose argument, right? It's just a strong law of large numbers. If you don't know, come on, guys. I thought you... SLL stands for the strong law of large numbers. S, right? All right, guys, so I would like you to do this homework when you have time. Right, the next thing I'm going to talk about is testing equality of variances, right? Now, suppose All right, assume the samples are independent of each other, okay, as before. So you have two independent random samples from two different normal distributions, right? And we want to test are you guys okay? We want to test whether the variances are equal. So it's the same as testing whether the standard deviations. Sigma x is standard deviation for the first sample. This is a standard deviation for the second, right? Yeah. So you have the three. You have the three rules. All right. For the first hypothesis, you reject H0 if right. This is the rule. This is the rule for the first set of hypotheses. For the second one, yeah, and for the third one, right? So these are the three rules for the three sets of hypotheses. Now, unlike the previous tests, these tests, sorry guys, what am I writing? These tests are most powerful tests. So these tests are really, they are most powerful. In other words, as I said several times, guys, most powerful means that you can derive these rules, these three rules, using the Newman-Pearson lemma, right? Okay. Now, I'm going to give you one more homework, guys. I know I'm giving you a lot of homework, guys. I hope I'm not being hard on you guys, right? You don't have to do all of them. I mean, I'm not going to test all these in the exam or something. Just, I mean, I know you're like, I mean, if you can't do this, if you can't do this, guys, just send me an email or come and see me if I'm in my office. Yeah, I'll be in my office throughout. Well, most of the time during the break, I will be in my office, except for the first week, I will not be, right? But even then, I will have access to email, so you can email me anytime. All right, derive pi for let me number this just a minute. It's 24. So this should be 25. This should be 26. This should be 27, right? So for the test, 26, 20, 25, 26, and 27. Now I'm gonna give you a hint. I know. I mean, it's not fair. It's not fair for me to ask you to do it without a hint. Now the hint is as follows. Now you know that Sx squared is the sample variance for the first sample, right? So you should multiply this by m minus 1 and divide by sigma x squared. What distribution you're thinking it will have and why? You should know this, guys. What's the distribution here, guys?
Chi-squared?
Yeah. Everybody follows this? Yeah. Chi-squared with m minus 1 because by equation, let me show you what this equation. If you look at equation 72 on page 16, this is where it is, guys. If you haven't seen this before, I'm sure you have seen this. This here, this is the equation I'm referring to, guys. Right? Okay. And similarly, yeah. Okay. Okay. Now what I'm going to do is the following. I'm going to, from this equation, guys, from this equation, you can write, you guys listen, please. You can write, you see what I've done here, guys? I have divided both sides by m minus 1. So you get this, right? You guys listen, please. From this equation, you get you see what I've done? I have divided both sides by n minus 1 to get this. Now, from these two, now, what I have done here, guys, is that I have divided this equation by this equation to get this, right? Now, can you tell me what distribution this is and why? I'm sure you should know. What is the distribution of this, guys? Yeah. This is what? This is the same as the F distribution with parameters m and n minus 1. You see why? Because, guys, look at this, guys. This is the F. This is one of the properties of the F distribution. Equation by equation 82, right? Okay? Yes. And therefore, what this implies, guys, is that Sx squared divided by Sy squared, right, will have sigma x squared divided by sigma y squared times an F variable. Now, you should be able to use this result. You should be able to use this result to derive the power function for test numbers 25, 26, and 27. So I mean, this is the result that you will need to use, right, to derive the power functions. Okay, guys, you need.
Is the square on the variance or on the x and y? I'm a little bit confused.
Over here?
Yeah, I mean the square is on the.
No. It's for this,
Yeah.
like this, yeah.
Yeah.
It's the same everywhere. It's just maybe.
What you are writing is like okay, it's like this.
Yeah. I'm sorry. I will correct it now. Yeah. Sorry about this. I thought. Okay, is that clear now, guys? Yeah. And the same thing here, guys. All right, guys. I hope it's clearer now, right? Okay. Any other questions, guys? So you should be able to derive the power function for these three tests using this result, right? If you have any problems, send me an email, guys. Okay. Right. Now, what I'm going to do now, because you guys probably remember, I did the, several times I referred to tests being most powerful. Now, I said most powerful means that the tests were derived using the Neyman-Pearson lemma, right? But I never did an example on the Neyman-Pearson lemma. So what I'm going to do now is to go back to the Neyman-Pearson lemma, which is this one here, guys. I hope you can see it. This is the Neyman. I talked about it before, right, in the class. So I'm going to do some examples. On I'm going to do some examples on the Neyman-Pearson lemma. The first one, let me look at the Do you have copies of this guide? This example 87. I don't know whether you can read it or not. Trying to focus this. Oh, here it is. Right, this is example 87 is this one, right? So you have and we want to test H0, which is right. Now, do you guys remember this distribution? What's this distribution known as? Huh? It's one of the distributions we talked about ages ago. This is the beta distribution, right? We talked about it quite a while ago. Right, by remember, the Neyman-Pearson lemma says, and you guys listen please, the Newman-Pearson lemma says that we reject the null hypothesis if the ratio of the likelihoods is less than a constant k. Now, the likelihood is the likelihood at theta 0 divided by the likelihood at theta 1. So it's the likelihood at 1 divided by the likelihood at 2 must be less than a constant k. Right? Now this is why you need to know the beta distribution. You guys remember the density function for the beta? I know it must have been ages ago, guys, but let me show you where it is. This here. This is the density function of the beta distribution, right? Now here we only have one observation x, so the likelihood is the same as the density function, right? So I'm going to use this with a1 equal to a, so it's going to be a plus 1 divided by gamma at a, gamma at 1, x. Sorry, a is 1. Okay, a is 1. Sorry, guys, a is 1. Then you have 1, 2. Okay, and you have x to the power 1 minus 1. Then you have 1 minus x to the power 1 minus 1. Do you guys see how I got this right? Just using this formula, guys. Because our a1, because we have this distribution. Can you see this? Yeah. A1 is equal to a and a2 is equal to 1. And under the null hypothesis, we are assuming that a is 1. So it's 1, 1, right? And L at 2, the likelihood at 2 will be gamma at 2 plus 1 divided by gamma at 2 times gamma at 1, x 2 minus 1, 1 minus x, 1 minus 1, less than a constant k. You guys see how I got this? Yeah? It's just using this, guys, right? Now, gamma 1 plus 1 is 2. What is gamma at 2? Gamma at 2 is equal to, remember what I told you, one of the properties, if you have n is an integer, then gamma at n is n minus 1 factorial, right? So gamma at 2 is 1 factorial, which is 1, right? So this whole thing is 1. And gamma at 3 is 2 factorial, which is 2. So this is the same as this. I mean, this whole thing simplifies to 1 divided by 2x, right? Yeah. And so I have simply used the fact that gamma at n is n minus 1 factorial. That's all I have used to simplify this to this, right? Now this is the same as x or 2x greater than 1 over k. So x greater than 1 divided by 2k, right? So this is, sorry, let me take this away. So this is the rejection rule. This is the rejection rule for testing the hypothesis that a equal to 1 versus a equal to 2. Now, but we don't know what this k is. I mean, how do we choose the value for k? Now, in order to choose the value for k, I'm going to use what is given to us. We are told that alpha, remember alpha is the probability of type 1 error, right? We are told that alpha is equal to 0.05. So I'm going to use that. Oh, sorry, let me copy. I'm going to use the value for alpha to determine the value for k. Now, we are told that 0.05 is the probability of type type 1 error, right? Now remember, type 1 error is the probability that you reject H0 given that the null hypothesis is true, which is, in this case, is equal to 1, right? Now we reject the null hypothesis if x is greater than 2. Yeah? Now we know that x is a beta random variable with parameters a and 1. Now if a is equal to 1, then what you have is a beta variable with parameters 1, 1 greater than 1 over 2k. Now, do you guys remember one of the properties? I'll show you in a minute. One of the beta distribution with parameters 1, 1 is the same as, yeah. Should go back here, guys. This is why I write this down, guys. If a1 is equal to 1 and a2 is equal to 1, then x has the uniform distribution on the interval from 0 to 1. This is one of the properties I mentioned to you ages ago. Right? So using that property, what you have is the probability that a uniform variable and this is 1 minus the probability that this is 1 minus. Now, you guys know the uniform distribution. You should go, there's another distribution we talked about ages ago. Let me show you. It's here. It's this one. This is the uniform distribution we talked about some time ago. Now, if your A is 0 and your B is 1, then the CDF A is will be equal to x, right? So what you have here is the CDF of the uniform distribution at 1 over 2k, right? So this must be equal to, yeah, do you guys follow what I'm saying? Because the probability that a uniform distribution less than or equal to, say, u is the same as u. Yeah, that's by definition of the uniform, right? All right, so this implies, guys, that 1 is equal to 0.05, and therefore 1 over 2k must be 0.95. Okay? All right, now going back to this question here. The question I asked here is how to choose the value for k. Now, we have answered the question here because we have said here that 1 over 2k must be 0.95. So if I call this double star, right? Right, by double star, so by double star, the most, now you can use the word most powerful because the test was derived using the Neyman-Pearson lemma, right? So by double star, the most powerful test is to reject the null hypothesis if x is greater than 0.95, right? Is that clear, guys, or not? This is the first example I'm doing. Although I talked about most powerful several times, this is the first time I'm trying to illustrate how to obtain a most powerful test, right? Is that kind of clear? Because you in the final exam, you will get a question you will get a question asking you to derive the most powerful test. So what that means is that you just need to apply the Newman-Pearson lemma, just like I did in this example, right? And obtain the most powerful test. Yeah. Any questions? Is I guess okay? Yeah. Let me. I know I've got a few. I don't know whether I have enough time to do one more example, but let me write down. Just maybe you can think about this during the break. Right? This is example. Example 88. Right here, it says that you have x1, x2 to x20 IID Bernoulli with parameter p, and you're trying to test whether H0, zero. So the question is to find the most powerful test of H0 versus H1, right? So this is a question. So you have a random sample from a Bernoulli distribution, and you're trying to test this versus this, and your alpha is given again as 0.05. So try to think about it over the break, and okay. And when you come back, I'll try to do it. If you can't do it, tomorrow we have 2 example classes. I would like more of you guys. If you haven't been to the example classes yesterday, please do come to the example classes tomorrow, right? And once again, if you have any questions during the break, please feel free to send me an email. I will respond to you as soon as possible. See you guys. See you. Bye-bye. Hi. Yeah.
So for this part of question, in your lecture note, it's greater than or equal, but sometimes.
Yeah, it doesn't matter because it's continuous. We are assuming x bar
But
is.
it's.
No, we are assuming x bar is normal. It's normally distributed, which is a continuous distribution.
X bar is always.
X bar, you see, we are assuming that x bar has a normal distribution, which is a continuous distribution. So it doesn't matter whether greater than or equal to mean the same thing, because we are assuming a continuous distribution. Okay. You understand, guys?
Yeah.
Yeah.
I want to know, can I get the result by check the table reverse?
No, you can't. You have to leave it like this because you cannot use the tables to read this. You have to leave it like you have to leave the answer like this.
Can I regard this as x, c, v, and check reverse because
You can do this in a computer. If you have R, for example, you know R, right? The software called R, you know, right? You can compute this using R, but not using the tables.
okay, thank
Yeah,
you
not
very
not
much.
using the tables. No.
Thank you.
Yeah. Hi, you have a question?
I have additional question for this. And
I will do it tomorrow. I did it yesterday in the example class. You were not there.
but another questions.
Yeah.
What if the true value for sigma is smaller than this?
No, that means that the alternative is not true. See, the alternative says that sigma must be greater than this. So the true value must satisfy this. The true value must satisfy this condition, right?
What if
it cannot be less? It cannot be less than, because it must satisfy this condition. Yes.
So if the true value for sigma not suit the condition of each one, we can't calculate type 2 error for this.
No, yeah, you can't calculate it.
Okay, thank you.
Hi. Hi, you have a question? Yeah. How are you? Yeah, it's normally like in statistics we say that if it is greater than 25, then it's fine. It's like a custom. You know? It's like a custom. It's a tradition. It's a tradition. Yeah. Yeah. Some people say 20, some people say 25, some people say 30, but it's normally around that. Yeah. 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 It's like, yeah. If you look at any books, they will say that. I mean, even in statistics, they say 20 or 25 or 30 is large enough. Yeah. Have a good break. Yeah. Have a good break, guys. All right. See you.